Part 3, Miscellaneous Proofs. In this particular section, I would like you to try to prove whether or not the given integrals converge or diverge using any method. Maybe one method works and another doesn't. Perhaps they both work. So you are going to do a little bit of work investigating this. So for example, A, the integral from 1 to infinity e to the negative x squared dx. Please press pause, take a moment, and see if you can find whether this converges or diverges, and prove it carefully using one of the tests that we have learned so far in the lessons up to this point. So it turns out that the integral converges by the direct comparison test. So we let f equal and g equal. We showed that they're positive and continuous on the interval. Then we stated that the integral from 1 to infinity of 1 over e to the x dx converges as the e integral. We defined that in this lesson. And because I'm using the direct comparison test, I have to show that f of x is less than the g of x, in this case less than or equal to, which is okay, and boom, so that satisfies, and therefore the integral of the integral of f of x converges by the direct comparison test. Now, had you tried the limit comparison test, you would have fiddled around with it for a while and had trouble coming up with a limit. So because you couldn't find a limit, that would have made you then try something else. Direct comparison test being that something else. Example B, same thing. Please try to prove whether or not the integral from 2 to infinity of dx over natural log of x converges or diverges using one of the tests that you've learned up to this point. Pressing pause now, or stay tuned for a hint. Hint. F of x. That's not your hint. Your hint is this. G of x is 1 over x. So it turns out that the integral diverges by the direct comparison test. Had you tried the limit comparison test, you would have found the limit as x goes to infinity of f of x over g of x to be unbounded. It would have gone to infinity, and then it would have been inconclusive. So this led us to the direct comparison test. So let f equals g equals, they're positive and continuous on the interval 2 to infinity. The integral from 2 to infinity of 1 over x dx diverges. That's our p integral with p equals 1. Then we showed that f of x, 1 over natural log of x, is bigger than 1 over x on 2 to infinity, because x is always bigger than the natural log of x on 2 to infinity. Because f is always bigger than g and the integral of g diverges, therefore the integral from 1 to infinity of f of x dx diverges by the direct comparison test. In example C, spoiler alert, we already know that this converges. What I would like you to do is prove that this converges by the direct comparison test. It'll work. And prove that it converges by the limit comparison test. It works. But I also want you to prove that it converges by definition. We've done all three of these somewhere in this lesson, in this unit. So let's see if you can't pull it all together and try all three tests to determine that this converges. The directions say, if it converges, find what it converges to. The only way we can find what it converges to is the definition. So just keep that in the back of your mind, that if it tells you what does it converge to, the definition is the only vehicle to lead you to that answer. What I'm going to show here is the definition. So make sure you press pause if you don't want to see it yet. Integral from 1 to infinity dx 1 over 1 plus x squared. This now is the definition. Limit as b goes to infinity, 1 to b, fast forward, The limit as b goes to infinity of the inverse tangent of b, that's going to go to pi over 2, and the inverse tangent of 1 is pi over 4. So the limit is pi over 2 minus pi over 4, or pi over 4 positive. So we know, because it came to a number, we know that the integral converges by definition, but we also know that it converges to pi over 4. That completes the lesson. That completes the unit.